Very good evening to one and all. Welcome our 30-day masterclass on advanced VLSI design and verification. Today our day 20. Today we are going to see a project of I2C, like a sender and a receiver, like a controller and a slave. So very good evening to one and all. I think my voice is clear for you. I'm audible to you. If my voice is clear means just put S in chat box. Okay. If my voice is clear means just put S in chat box, then only I can know that is my voice is clear for you. And then we will start the coding part of today, I2C. Before going to that, we will see the what is the clock stitching. So clock stitching is very important, and also I shared the attendance link for the yesterday class. So again I will share the once again, just copy the link, like copy the Google Form link and then put into your browser, then you will get the form, attendance form. Okay, Google Form. Okay, thank you for your response. Bharat Raj Singh, Narayana Murthy, very good evening. Naveen Rati, very good evening. Nikesh Tota, very good evening. Steve Satya, very good evening. So today we are going to see I2C. So you are audible. Thank you for your response, Naveen Rati. So before going to start, let's wait for a few minutes, then we will start. So main thing of I2C is it is an off-chip protocol. We can interface the peripherals, like a LCD module or any CAN protocol, any other sensor, and then it is a speed. It is high speed protocol only. So it is high speed means it is more speeder than UART. Okay, compared to UART, it is an high speed. Okay, let's see in the session the I2C design and the test bench code. Okay, design code for controller like I2C master and then I2C slave. So we are gonna write the Verilog code for two things, I2C master and then I2C slave. Okay, in the I2C master, assume like the master is controller. So any controller, like assume like Arduino controller. Okay, Arduino like a ARM processor, any controller, and then slave is a LCD module or any other slave peripheral devices. So firstly the master will initiate the process by pull down the by if you are multi-master multi-slave means there is a process of arbitration. So one which master want to communicate with slave means that particular master firstly pull down the STA line, like a data line pull down, then only that master will get the access for I2C bus. Okay, so there is a race between the who will firstly pull down the I2C data line. If you that like that particular master will win the this process in the arbitration means that master will get the access of I2C bus, then it will make communication between the master with the slave. Okay, so very good evening to one and all, thank you for your presence. So and then I2C act as a master under what conditions? So I2C, so it is our logic only, so we can assign any controller, any processor. So assume like a FEJ, so FEJ1 controller like FEJ Arctic 7 or Max 10 FEJ or Xilinx Spartan 3 FEJ controller. So Spartan 3 is a one chip, it is a controller, so it is act as a master. The slave device is I2C module LCD. So I will show you the picture of the I2C module. So I will show you the I2C module LCD. Okay, so you can see here. So this is I2C module. So I2C module of LCD. So it is act as a slave. The main controller is Arduino. So for example, I am telling Arduino is a main controller, master, slave is a LCD module. So LCD, this kind of hardware. So the Arduino controller will send the data to the LCD slave. Okay, LCD module slave. So the LCD will receive the data from controller Arduino, and then it will display the data in LCD. So it is how it works. It is a basic example for I2C master and slave. Okay, there are two pins only, STA and then SCL, data line, clock line. So it will send one by one bit. So it will send first the start bit. So yesterday we see in the frame format of I2C, start bit, address, and then read and write bit, and then acknowledgement from the slave, and then data bit, and then acknowledgement from the slave, and then another data bit, and then acknowledgement from slave. So it will continuously doing by one by data bits. After the end of the data packets, the master will send the stop condition. Stop condition means there is a combination of there is some logic from between the STA and the SCL. So while clock is high, like a SCL is high, means logic high. From that on that time, the STA line, so STA line will changing from 1 to high to low. It means it is a start condition. So yesterday we seen that the start and stop condition of I2C. Okay. So I think it's clear for you. Today we are going to see firstly the main thing is clock stitching. So yesterday I received queries about clock stitching. So what is a clock stitching? So it is nothing but, so is that processor when send the signals to control peripherals. Yeah, so it is a off chip protocol. Off chip is nothing but outside the chip we are communicating with the peripherals by using this protocol. Okay, it is a off chip protocol. So very good evening, Tarun, Vasu, Vaishnavi, and then Srinivasa, Sampath. Okay, thank you for your presence. Thank you for your daily presence. So main thing is what is clock stitching. So assume like I am the master, you guys are the slave. So I am communicating with you, I am speaking to you. So I am speaking to you means you are listening to me. But if you need some time to process my words, process my content, you need some time. So on that time you will just pull down a SCL like a clock line like this. Okay, so it means the slave will take some time while doing the process of pulling down the SCL line, clock line. So if it is doing means there is no passage for, there is no condition, there is no access for the master to send the data to slave. Why? Because of the slave device pull down the clock line to active low 0. Okay, so you can see here there is a clock line, data line. So on that time, so SCL you can see here there is only a little bit time, a little bit having the time of active low. Low means 0. So it means pulling down the SCL line into to the 0 means the slave needs some time to process the data which is received previously. Okay, so this is, so for that conditions, for this reason, like a slave needs time, and then there is an error means, and then there are a lot of issues means, the slave will control the communication flow. Why? Because of if any problem with the slave means, if you are the master will sending continuously, so totally it will give the wrong communication. Slave needs correct input, correct data which is sent by the master. If any issues happening means, the slave must be slow down the process. For that time the slave device will doing the clock stitching. The slave device will doing the clock stitching. Okay, this is the clock stitching, pulling down the SCL clock line. Okay, so why it is pulling down means, we know that that I2C bus like a STL, STA, SCL, data line, clock line are circuit connected with open drain circuit. It is always high. So it is always high. So any devices can pull down the STA, SCL line. Okay, this is the main thing. So any devices from master side, from or else from the slave side, slave device, or from master device, any devices can pull down the lines. Okay, so by using that technique, by using that advantage, the slave pull down the SCL clock line to take some time to process the data. Okay, so this is a clock stitching. It is mostly used for synchronization between the master I2C, slave I2C. So slave device, master device, slave device. For some reason slave needs some time to process data, or else to or else the master device is faster, like it having the high clock frequency, the slave device working with the low clock frequency, and that time we can use the FIFO buffer also, or else and also we can use this clock stretching for the synchronization between the master and the slave devices. Okay, I think it's clear for you. So yesterday I received some query from this some class stretching only, that's why I'm telling this. So I think it's clear for you guys. If you have any doubt, in the class stretching means, just put yes, just put a question in chat box. Okay, it is very important, class stretching arbitration. So arbitration is nothing but process of getting the I2C bus. It is a competition between the master who will get the firstly access for the I2C bus. I2C bus is nothing but STA SCLN is a I2C bus. So arbitration is nothing but who will get the access for the I2C bus. It is an arbitration. Clock stretching is nothing but a slave device will pull down the SCL like a clock line to low to make the synchronization, and then to take some time for data processing. Okay, I think that's clear for you. So and then we'll move into code. So you will get the link of Bharat Singh. Okay, so and then this is a I2C basic information. Okay, I2C basic information. So yesterday we also seen the standard speed modes, and then basic informations. So both lines are open drain, open collector, meaning devices can only pull the lines low. Okay, to drive them high, to drive them high, and pull up resistors are used. By using the pull up resistor is always active high, so you can master devices or slave devices are only capable to do the pulling low the lines. Okay, so because of the open drain structure, the multiple devices can share the bus without conflict. Okay, by using this technique like a open drain structure, multiple device can share the bus without conflict. If any devices pulls a line low, the line stays low. Okay, it means while pulling down the line slow means is nothing but that master saying the I2C bus, I want to communicate with the slave, so I will take the I2C bus. And then if the master completed with that process, and then it will pull high, it will give the pull high for the I2C bus, and then another master will take the chance to process to send data with the slave device. So this is how it works. So and then so this is a process of clock stretching, arbitration, and then for open drain circuit. Okay, start clock stretching is nothing but the slave device needs some time, so it will do pull down the SCL clock line too low, so it to take some time. And then arbitration is nothing but it's a competition between the master who will take the I2C bus. So if you want to, if the particular master want to take the I2C bus means that master device must do the pull down the I2C line, like I2C data line, then only it will take the I2C bus to communicate with the master. So this is a main difference, main thing of the arbitration, clock stretching of I2C. So and then we'll see the code today. So firstly, main thing is I will tell you the logic. So I2C master is assume act as a controller, I2C slave is act as a any peripheral devices. Okay, I'm going to write the two code for that, I2C master code, I2C slave code. Okay, master is a controller, and then we can assume like a slave also on controller. So it is a controller to controller communication between the by using the I2C protocol. So controller will the main controller, like a master controller will send the data to slave controller. So how it will send means, firstly it will send the start condition, and then it will send the slave controller address with the read or write bit, and then it will send the and then slave device will send the acknowledgement to the master, and then master will after the acknowledgement the master will send the 8 bit of data to slave device. So and then if the data is received by the slave device successfully, there is no error means the slave device will send the acknowledgement to the master. It's like I'm getting the data correctly, you can send the next 8 bit of data to the it's like a telling to the slave to master. So and then if the master receives this message means acknowledgement means the slave will send the master will send the another 8 bit of data to slave, and then slave will again say I'm getting the second I got my second data, you can say you can send the next data by using that acknowledgement bit. It is like working. So it is slave device is telling to the master, so it will continuously working up to the end of the bit. If the master sends all the data bit means, and then it will finally to stop the simulation means to stop the communication, the master device will send the stop condition. Okay, this is how it works. So this is a main logic. So firstly I will send the one data to slave, and then I'm checking the test bench, so whether my sender data and then my received data is correctly. So whatever I send it in the master, and then I must have to receive in the slave device, then only my process of I2C communication is working correctly. I'm going to check this only while I'm going to write the logic for whatever I'm sending the data to slave. So the slave must be receive the correctly must be receive the same data which is sent by the master. If it is both are matching, master sender device, slave receive device, both are matching means I can say that my I2C communication is working correctly. Okay, this is a logic I'm going to write today. Already written today. So this is firstly I will start with the controller like a master. Okay, so this is a master. So we know that while writing the design code, firstly we need to make the FSM. So FSM is nothing but final state mission. So we need we have some goal. So we have to divide the process by using the state. It's like a state. Firstly, start condition is one state, another is address condition is another state, and then read or write another state, acknowledgement is another state, and then data we are sending the data from master to slave is a third state. Sorry, it is also one kind of state. So we are having a lot of state like a start state, address state, read or write state, acknowledgement state, and then data state, acknowledgement data, acknowledgement, it will goes continuously, and then stop condition is the last state. So we need to declare firstly state, and then we are saying what we have to say, we have to write the logic in the each state actually what it will do. So that logic we have to write inside the each state. So basically we are doing a state transition from one state to another state sequentially, like a start state, address state, read and write state, and then data state, acknowledgement, data, acknowledgement, stop. So it will flow like this only. So it will start from start and it will end from end state. So firstly we need to declare the state, and then we need to declare the IO signals, and then the main IO signal is only two signals, STA, SCL only. So and then we have to declare the internal signals for the um, for the logic. So and then main thing is controller is one device, slave controller is also one device. So from the both devices it having some memories. From the memory only the controller will send the one bit. Same slave also. The slave which is received from the master, it will store one bit in the slave. So firstly we need the create IO signal, memory means to store the data, and then FSM. So this is a kind of logic we're gonna see. So open drain here. So open drain circuit is nothing but that circuit will make the STA SCL line is always active. So I will show you the circuit here. Open drain circuit. By using the pull-up resistor, it is always are in the active state. It always having the 5 volt only. So by using the VCC pull-up resistor open collector, so it is always having the active high. If the any input, if it is 0 means it will so if based on our input only it will open the it will make the flow of the discharge of voltages. Okay, this is how it works. So by using the VC, you can see here VCC and then pull up resistor over here. So at the initial starting stage of time, that two lines, STA line, SCA line, having the high value only, like a 5 volt only. Okay. To if you want to pull down means you have to open this circuit. You have to give the input supply base input for the this transistor. Okay, BJT transistor. So it's emitter collected. So if it is open means, so that here we have in the ground, so it will open the circuit, so it will automatically discharge the current. Okay, so if you if you pull down the ST elements, you will get the access. So that if the particular master is doing the pull downing of the I2C bus, like a I2C lines means, that master will get the access of getting bus access, I2C bus access. Okay, same for the clock stretching also. The slave devices pulling down the clock line. So clock line also, so you can see here in the clock. So this is a basic thing. I will show you in the picture. So you can see here. So this is controller device 1, device 2, device 3. So each and every this is a master, three slave devices. This is a first device, slave device, second slave device, third slave device. This is a this is a master. Okay, master I2C. So all these peripherals, like devices, are connected with only two lines, only one bus, I2C bus, SCL, STA only. So each and every these two lines are always having high. Why? Because of we are using the pull-up resistor with the supply of 5 volt. Okay, so if you want to if here is a transistor circuit over here, if you want to open means you have to open the transistor. If you want to give the current required threshold current for transistor, and then it will open. So it will open the flow, and then it will do discharge of charges like this. It will discharge of charges in the ground here. So and then you will get the access. The master will get the access of I2C bus, and then it will send the start bit, stop condition address, and then it will do continuous data transferring. So how embedded in this code application using controller, or we need to design the chip can control the entire. So while doing here in the I2C, in the FPGA we can control by the hardware. So we can control by the VHDL or HDL code. So for example, so we know that just a minute. So we know that any controller, like a FPGA is also a controller, but it is like a fully we can customize. So we can customize the FPGA controller. It is a reconfigurable. It means each and every pin of the FPGA we can do reconfiguration. So we can assign the two pins for I2C, SPA, any other UART. But if you are coming to the processor, like a microprocessor, they are fixed. We can't change. So in the for example, in the Arduino, if you take any PIC controller, any other ARM controller means ARM Cortex controller means, they will made some circuit, open end circuit in the PCB. So in the chip level they are made some circuit that two pins only for the I2C only. So there's a circuit in the controllers, but in the FPGA side, in the FPGA part, we can control that pins by this code, by using the HTL language, Verilog or SystemVerilog. We can control the open drain combination, like a open drain logic, low high. See, these we can control by the code in this FPGA, but you can't do in the controllers like a microprocessor. Why? Because of they are comes under the ASIC chip, so you can't do customize, you can't do reconfig. If it is made, if one IC is made means that is only for that particular task. You can't do any other, you can't do anything in the ASIC chip. Okay, FPGA means it is like a baby. So like we can, if you say something, if you want to say, if you want to act like any other means, you can make it in the FPGA. It's like reconfigurable. So that this is a main difference between the FPGA with all other chips, like FPGA chip and the other chips. Why? Because of FPGA is a fully reconfigurable. So Verilog code. So like you are telling like a C code and then embedded C Python code. We can control in only the uh, like a Arduino board, pick DS pick and then ARM Cortex controller or any other embedded boards only. But in coming to the VLSI, so if you literally seeing if you want to see the depth knowledge in the chip, we have to write these controller combinations inside our chips. Okay, so coming to the on-chip protocol, you will get the idea about the protocols. So I'm main thing is Verilog code. By using the Verilog code or SystemVerilog code, you can make the hardware. Okay, you can make the hardware with the help of the transistors. By the in the you can if assume like a Arduino chip, Arduino having one IC, so which is it will do it having some embedded ARM Cortex processor or any other processor it having inside the chip. Okay, that ARM Cortex processor it having some computer architecture, and then that architecture is which is developed by the various engineer only. So it having some blocks, it having some arithmetic logic unit, control unit. So inside the control unit and then arithmetic logic unit, it having only transistor only. So literally the chips are works with the transistor, which is we can by using the HTL language only we can control the chip. So after this making of this controlling chip, and then we are after writing the design code, they will make the physical chip with the help of computer architecture. So from the computer architecture only our assembly code and then embedded C code, embedded C assembly language, machine language, it is executing based on the computer architecture only. ISA like instruction set computer architecture, based on that only the microcontroller microprocessor are working. But in the FEJ there is no need for the computer architecture, there is no need for assembly language. So only one language is Verilog. By using the Verilog language we can easily control the FEJ. Why? Because of inside the FPGA chip, it having only transistor. It is only having the empty transistor. That particular transistor they don't do anything. So if you write some logic in the Verilog, we dump into FPGA means it will do the logic whatever written in the Verilog code. But now other chips like ASIC chip like SOC, processor, i5, ARM processor, ARM Cortex, M series, DS PIC processor, that all different. So it is a prefixed only. It is only they are made for only only for specific task, not for the reconfiguration. They only made for specific task only. Okay, this is the main difference between the FPGA and the controllers, PIC controllers, ARM controllers kind of thing. So then coming to the code. So these are the input and output signal of my I2C master. Okay, so I have a vertex board. Can I use as control generating code? Yeah, you can. If the vertex board is in FPGA means you can use the same code. You can assume like you can implement, you can write the master code and then slave code in your FPGA. Okay. So and then this is my input and output signal of my controller, clock, reset, address, data in. So we need the address and data enable, and then read and write bit, data out, and the ready signal for my handshaking technique. And then I was so in out means, so it is a off to flex. So it means it's like a only we have it having only two lines, whether master send to the slave send to master, so that I'm using the in out. Okay, so and then these are my states. Okay, ideal state you can see here. Ideal state, ideal means initial reset condition state. Start is a one state, address is a second state, read acknowledgement is another state, and then write data is my another state, write acknowledgement is another state, and then read data is another state, and then read acknowledgement is another state. So and then stop with my 8th state. So I'm having the 8 states. Why? Because of we know the frame format of I2C: start, address, read or write, acknowledgement, data, acknowledgement kind of thing. So and then this is some parameter divided by 4, and then this is my state. This only I'm going to use for the state transition here, and then saved address. So I want to save the slave address, so that I am using some internal, these all the things are comes under the internal signals. To make my code logically working means I need some temporary internal signals, so that I am creating this kind of signals. So and then this is my main assign statement for my control logic. Ready means if the reset is low, it means I'm going to use active low logic. So if the reset is low and then state in the idle state, so ready signal, so that ready having the high. If the state, if my reset in the 0 and state in the idle state, my current state is in my idle state, means I am assigning the 1 value to my ready signal. Okay, same like I2C SCL clock line. So if the enable is low, means it will give y, it will give 1, or else it will give the I2C clock. So I2C clock, here I'm creating the I2C clock here. So it will do toggling. So I'll tell you one by one. So and then data line. So for write enable is high, means write enable, it means I can write the data. So master will write the data. So STA out will give the STA out, means I'm storing the some signal. So it is my signal. I want to send the master to slave. So and then these are the logic I am written by the ternary operator. So I know, I hope you guys are aware of the ternary operator. If the condition is true, means it will choose this, like this one. If the condition is false, means it will choose this one to assign this particular signal. So and then here I'm toggling the here I'm doing the creating clock. So divide by 4 by 2 means 2 minus 1. So at every one count I'm toggling my clock. Okay, so here I'm increasing my count. So and then same here in the reset, if the reset condition is high, means I'm just off my enable state. And then if the state is ideal and then state is in start and then state is stop, means and in the same like these logics are having true, like state in the ideal state and then state in the start state and then my current state in the stop state. If it is happening, means I'm just off my enable condition. Why? Because of I can't be in the all the state. In the ideal state I can't be, that the particular controller are not currently in the ideal state, start state, stop state only. Why? Because of there is only one state, the current state will be working. So it won't work in the all the state in the same time. So in the same time it can be in the only one state, either idle state or start state or stop state, address state, that only. It can't be in the one or more state in the same time. Okay, so and then this is a logic for that. So it is a very simple code. So if you are while writing the SOC level, chip level, or any other high level code, means there is a additional logic, additional timing issue. So I know we already seen the speed of the I2C. So it having the 400 kbps, 400 kilobits, 800 kilobits, 1 megabits, and then 5 megabits. So this depends on the clock. So how we optimize the clock? So by using the counter we can optimize the clock speed. So we can increase the clock speed. So okay, and then this is my state. So this is my state, this is my ideal state. So in the ideal state I'm just I'm staying in the ideal state. I'm staying, next state is a start state. And then you can see here, by using the concatenation I am storing the address and the read and write enable. So I am just combining the address and then read and write bit. Okay, so totally 7 plus 1, 8 bit to my saved address signal. So and then I'm storing my data into my saved data. So and then I'm going to it will going to the start state. So counter is a 7 state in the address state. If the counter equals to if the counter equal to 0, means it will go into the read acknowledgement. So and then from the if STI is 0, so it means the I2C STI line having the 0 means. So I'm just saying that write state. Okay, just a minute. Okay, if the save address, you can see here, if the save address of 0th index, it means last 8th index. It means if it is 0 means I can write into I can move into write state. If it is 1 means I can read. Okay, so it means that 0th index is nothing but it is my read and write bit. If the read bit, if the that read and write bit having the low means I can write. Okay, if having the 1 means I can read. So this is a logic, this is a write. So this is a write data, this is my read. In here I'm doing the read acknowledgement. So and then here I'm doing the read data. So and then I'm going back to, I'm wait for the write acknowledgement, and then in the write acknowledgement state I'm going to the stop state. In the stop state I'm going back to the my idle state. I'm waiting for the another bit. Okay, this is how I2C master will work. So and then I2C slave. So I2C slave device, the address is nothing but this only. So and then these are my see internal signals of my I2C slave controller. So here also I'm having the same state, like a read address, read send acknowledgement, read data, write data, and then send acknowledgement to. Okay, so same here in the ideals, in the neckage of STA I'm staying in the start state. So and then in the passage of STA I'm saying that if my start is high and then SCL is also high, it means I can move into read state. So I'm telling some logic here. So and then I'm moving to my main FSM in the read address. So I'm assigning, so in the read address I'm assigning the STA, it having some values, I'm assigning to my the address. So and then if the counter reaches the 0, I'm saying that your next state is acknowledgement state. Okay, reading, so reading means receiving the data from the master. So by using the control I can, by using the counter I can move into the states. So same like, so it's a send acknowledgement. So address like a 7 down to 1, and then address if both are matching means counter is 7. Counter I'm assigning the value for counter is 7, and then my address is 0 means I'm moving into the, you can see here this address 0. So address of 0 means is my read or write signal. So read or write bit, if it is having the 0 means I'm saying that I'm saying to the slave you have to move to the read data. So here it will do the read operation. It is just simple only. By using the if else condition I'm changing the state, and also I'm telling some the inputs, like based on the read and write bit I'm telling whether where we have to go, write state or read state. Okay, so and then after that, where we are after the read or write operation, where we have to do, where we have to go, write acknowledgement or read acknowledgement. So based on this only it will work in the FSM. It is very simple only. If you guys have any time means you just listen this, see this code, you can easily understand. It's a simple code only. So you can see here and this ST out. Okay, so data out plus counter. So by using the counter I'm storing the I'm assigning the values from the data out to ST out. So data out is my internal signal, ST out is my output signal of my slave. Okay, so this is how it is simply, it is how it is working. So and then this is a master and slave code. Okay, so and then coming to the test bench. So test bench is nothing but we having the master code, master I2C master code, and then my I2C slave code. So we have to instantiate these both code inside my test bench. Then only I can pass the inputs for the slave. I can pass the inputs for my master, and then master will send the data to slave device. So the slave device will send the results to my test bench. It's like a flow. So firstly main thing is I want to instantiate the master code, slave code inside my test bench. So it is a top file. So why I'm doing this means, so I want to display my output, I want to do my simulation, I want to see my output in the transcript, in the console I want to see my output. So firstly I want to send the data to master. So master will send the data to slave. So from the slave the test bench code will fetch the data, will get the data from the slave. slave code in the test bench. So this is how it works. So say for that reason I'm instantiating the master code and then slave code. Okay, after that I'm creating the clock over here. So and then this is my signals for my test bench. Same signal, clock, read, reset, address, data in, enable, read or write, data out. So and then here I'm doing some simulation process. Firstly I'm initialize the simulation, reset equal to 1, address 0, data in 0, enable 0, read and write 0. So and then applying reset, so reset is 0, and then of my reset is a deasserted. So and then this is my address, this is my data which is I'm going to return for the slave. So and then write enable is 0. So and then write here you can see here starting write transaction. So I will display my the address and data in. So and then write enable is 0, enable again enable is 0, wait for the read signal. So wait. So the wait is here one kind of function we can it is like a function, so it will wait for this. So if it is ready signal is triggered, so it will execute, it will allow to execute this line. Okay, so again I'm doing the read operation. So write enable is high, you can see here write wr equal to 1. It means I'm saying that you can write into the master to slave. Okay, enable is high, and then I'm this is my display statement of the read output. So and then this is my test case 1, this test case 2. So and then wait for ready signal. So after that I'm displaying the final read operation complete, data out, and then simulation. This is my display statement for to end the simulation. So and then I'm here, you can see here I'm in the inside the initial begin. I'm using the dollar monitor to see the all the datas, so all the captured datas. So dollar display is nothing but it will display only the current values, so current values of signal. But here this dollar monitor will capture the all the changes which is happening in the simulation, which it will capture, and then it will send into the display statement, it will send into console. Okay, this is how it works. So and then this is my run.to file. So in the vlog I want to add all the file names, like all the file names exactly, test bench name, controller, I2C controller, I2C slave controller, and then I2C slave controller, I2C controller, I2C test bench. Okay, and then in the vsim I want to simulate the top file is nothing but my test bench file. So test bench module name I want to write in the vsim. After the vsim I want to write this, and then this command only used for add the waveform. So add the waveform in my Costa sim tool, simulation tool. So and then run -all is me, it's nothing but I'm saying to the tool run all the simulation files. Okay, so and then I'm going to the run this. So okay, so this is my slave. So so I just close this, I will just open again. So in the terminal, or else you can also follow this method. So this is my working directory. This is my working directory. In the address bar, just delete this and then type vsim. It means it will automatically open the Costa sim in my current working directory. It is a simple basic way to open the Costa sim in your current working directory. So and then here, and then in the Costa sim command line console transcript, just put ls to list the files, and then write do run.to. So it will execute the run.to file, saying in the run.to file we have declared some instructions to execute for the Costa sim. So it is doing simulation. So and then just click no. So this is my simulation output. You can see here I am receiving a lot of outputs, like a clock, reset value, enable, read and write, address, d in, the d out, sta, sel, ready. Why? Because of I am using the dollar monitor. So if any changes happening in my signal, means a dollar monitor will catch that values and then display in the console. So this is how it works. So firstly we'll see the applying reset. So and then firstly we'll see the first condition. uh, Starting the right transaction, address is 10101010, and then data is 10101101. This is my right address, this is my right data. So there you can see here I'm correctly writing in my correct address, and then D in also correct only. So and then these are the chunk values after the simulation. So and then write operation completed, and then ready equal to 1. So you can see here ready equal to 1. So read operation completed. So you can see here read operation. So you can see the output like a Z01110011. So this is my output signal. So what I am written into my address D in, I am reading from that place. This is my output signal. So ready is 0. So this is how it works. So this is how we can verify the I2C simulation. So and then write enable is 0 or 1. So 0 means write write enable WR. If having the 0 means I can write into the master to slave. Read means read operation, it will do the read execution from the slave device. So this is how it works. This is how I2C module. This is a basic simple basic code. So this is how it works. So I think it's clear for you. So if you guys are really interested in this masterclass, you can convert into 1 month of internship on advanced VLSI design and verification. So I will show you the process of getting the internship program. So by using this link you can get the internship program. So our regular fee is nothing but just regular fee is 4,999, but in the masterclass period we are providing this course at just 999. So you will get these benefits at end of 1 month of internship. All 30 days PPTs, downloadable codes, exclusive 4 projects with the I2C UART also, and then you will get the 180 days of LMS course access. You will get the assignment task we are providing weekly. So and then you will get the internship report. If you are studying the college student means it is helpful for you. And then you will get the high valued IETE certificate from the internship certificate from IETE. So it is a central government institute like NIT. So and then this is the benefits you will get at end of 1 month of internship. This is a registration link for the internship. So this is a limited time period offer you will get by that just 999. So and then by using, if you click that link means you will see this window, and then here in the domain you have to choose advanced VLSI design and verification. Okay, so then this is a sample certificate you will get at the end of the 1 month of internship. Okay, so and then this is I2C guys. So if you guys have any doubt means you can ask now. The main thing is clock stretching, arbitration, and then frame format. So this is enough for the I2C. So coding part, if you are really interested, you can watch the code. You can understand easily. The main important thing is you have to take your mind is clock stretching, arbitration, start condition, stop condition, frame format, and then acknowledgement process, and then data bit is 8 data bit, address bit is 7 or 10, one read and write bit. So this is the main thing of I2C. So and then thank you guys. If you have any doubt means you can ask now. So if you have any doubt means you can ask now. Okay, thank you guys. Thank you for listening. We'll see tomorrow with a new topic.